So basically with this one, it gives you, I'm not going to go all the way through this. It's pretty time consuming, this kind of problem, but you know, if you're told that an object moves along like a surface with that follows the function, you know, y equals x squared, say, from right to left. With the speed, I think in the weekly assignment it's a constant speed. Let's say this is a constant speed, 5 meters per second. You know, what's the acceleration as a function of x? And so the way you do that is first you come up with a parameterization. So the position parameterized by x is x squared. And then a vector that's tangent to the path, I'm going to call it u, at any x value is, you know, it's always going to be plus or minus the derivative of this with respect to the parameter. If it's going from right to left, we're going to take the negative of that. And so this would be 1, 2x, negative. Okay, so that's in the direction of the velocity vector, but it doesn't have the right magnitude for the velocity vector. So now you'd have to come up with a unit vector in that direction. And you do that by, you know, this is equal to 4x squared plus 1 square root. And so then the unit vector is negative 1 over square root of 4x squared plus 1, and then negative 2x over square root of 4x squared plus 1. And so then the velocity vector as a function of x is this times the speed, which in this case is constant, so negative 5 over square root of 4x squared plus 1, negative 10x over square root of 4x squared plus 1. And now you're finally ready to do the chain rule thing, you know. So the acceleration as a function of x is equal to dv dx dt. Okay. All right, so I'm going to stop there because that's where the derivatives start getting really ugly, but that's how you'd go about it. And then once you calculate the acceleration, the net force is just that times the mass. Any other homework questions? Yeah.
I just had a quick question on number 1 on the homework. It was like the triangle, the x bar, y bar.
Yeah.
It was just like to find it's just the base divided by 3 and height divided by 3.
Let me look at it. So that is rigid body kinetics.
Because the notes didn't seem to like go directly with like you did the opposite on the notes than you did on the solution.
Oh,
so
this one, finding this centroid?
Yeah, just the triangle. Is that like the x bar for the base and the height? Oh yeah, 1/3 from the corner.
Okay, so there's always a million ways to do these. I guess I would probably, my first thought would be to break it up something like this. And you also, there's infinitely many places you could put your coordinate system and orientations of the coordinate system and stuff. This is 1. So that makes the height of this triangle 2. And so, like, for the centroid, so let me number these. Let's call this body 1, 2, 3. X1, Y1 bar. So the centroid is 1/3 of, so if you go to the, go to the right triangle, in both, along both legs, it's 1/3 of the length. Okay, so it's going to be, in the X direction, it's going to be 1/3 of a length of 4. So that's 4/3 in the X direction from the origin. And in Y, it's going to be 1/3 of 2, but that's from this black dot down. So that's, so going up, it's going to be, well, this is 2, so it's going to be 4/3 up. And then the area of that triangle is the base times the height over 2. Yep.
So it wasn't the height of the whole, like just the triangle, it's the whole figure? Like when you're trying to find the...
Yeah, it's the height of just, I mean, you're doing these piece by piece, so all we care about is that triangle for this one.
But wouldn't the height of it be 2, or like the Y direction?
For the, for calculating the area, but if you're,
No, I was talking about the
The
Y
Y,
bar.
Y bar.
Y bar.
Y bar, okay, so for this, so for this triangle, we know that this distance, so the centroid is here, right?
Yeah.
And we know that this distance is 1/3 times the height of the thing, which means that this distance is 2/3 times the height of the thing. And this is 1/3 times the base, which means this is 2/3 times the base. So it all just depends.
Well, so you always take that so you're finding it from the point, the right angle on the triangle.
Yeah, it's always 1/3 of the length from the right angle.
Okay.
Yeah. And so then you have to think about where you're.
That's the flip side from the point, from the.
Yeah, I mean, you always are trying to calculate your distances from the origin. So, you know, you're not always going to use that 1/3. Any other homework questions? Okay, so let's get into, we're getting pretty close to being able to calculate, to do rigid body kinetics. So remember that before we got into problems, we had to define the center of mass, the mass, moment of inertia, about a point, and the moment of a force about a point. And we've talked about this one and this one, so now we're talking about the moment. And, you know, when I talk about it out loud, I just call it a moment. Everybody does. But remember that this moment is defined by the force and the about point, okay? So it's the moment of a force about a point. Okay, so let's say that this is some random object, and there are two relevant things here. There is this point A, that's your about point, and there's this point P where a force is applied, and you know, this is some unknown force vector. This is the force, the location P. And the first thing we have to define is this row vector. This is another thing that is absolutely going to show up on lecture quizzes, being sure that you know the definition of that row vector. The other thing that shows up on lecture quizzes all the time that, you know, sort of similar conceptually to this is that R vector for the watermelon equation. Okay, so be sure you can rattle off those definitions. So this row vector is the vector that starts at A and goes to P. I missed. Okay, good enough. So this is the row vector. And to calculate the row vector, you can always do that as the coordinates of P minus the coordinates of A. Okay. Then the moment about that, you know, around that about point A is equal to the row vector crossed with F. And remember, order of cross product matters, so if you do F cross row, you'll get the opposite thing of what you want. When we get to rotational Newton's second law, you're going to be adding up the moments produced by each force on the body. And so to organize these, I always write these out in a table. And the table looks like this. Everybody who did statics with me has seen this stuff. So we'll do it as we have a column for the row vector, a column for the force vector, and a column for the moment. And this row vector, you could always calculate this as P minus A. And the moment vector, you just calculate as row cross F. And if you fill this out, each row is a separate force. Let me actually generalize that and say each row represents one load. A load can be a force or a couple. Okay, and so once you're done with this, you have all of the forces in the middle column. You can use that for the left side of Newton's second law. All of the moments in the third column, you can use that for the moment equation, and it just makes it really easy to fill out your equations. For most of this class, at least, we'll almost entirely do this for planar problems. And so, like for example, a row of this would look something like this. You got the row vector, force vector, moment vector. And let's say you're doing this for the force F1, 2. Let's say the row vector is 5, -3, 0. The force is 400, -800, 0. The cross product, if you take that cross product, you get 0, 0, -2800. Okay. Well, remember that like all rotational vectors, the moment is parallel to the axis of rotation. Okay. And so if you're doing stuff in the plane, you're only going to have a z component for your moments. And so you should remember that this is what a moment means in 2D. It's a z component. Moments are always vectors. But you can, save pen strokes or whatever by just writing it like this. And I will do this all the time. Just write the row vector as 5, -3. It's in the plane, so z is always going to be 0. The force vector is 400, -800. And if you take that cross product, you get -2800. The thing is, just remember that's not really a scalar. It's not really just a number. That's a z component of a vector.
So we always do z.
Yeah, when you're doing problems that just exist in the xy plane, the moments are always just z components. That's just the way the cross product has to work. I mean, so if you're working in the xy plane, the row vector and the force vector only have x and y components, right? That makes sense, right?
Because it's a cross product, so it's
Yeah, well, so that's what I was going to say next is, so if rho and f are only in the xy plane, the cross product has to be perpendicular to both of them. So there's only two directions that are perpendicular to two random vectors in the xy plane. That's a vector in the positive z or a vector in the negative z. Okay. So for us, you can write it like this. Just don't be sloppy with your thinking. Remember that moments are always vectors. And what that -2800 really means is a moment vector of 0, 0, -2800. Okay. A special moment. I just wrote that song. A special kind of moment.
You write songs?
I just did. So my first one. I think it's pretty good. So what do you think is, people who took statics from me, what am I going to say is a special kind of moment?
Chase.
A couple, yes.
Just sounds, right?
Yeah.
I don't remember what I had for lunch yet.
Yeah. So a couple is a special kind of moment. What makes couples special? Well, what is it? Most half of you don't even know what a couple is, but a couple is a moment produced by two equal and opposite forces. Now, in general, the moment of a force about a point depends on your about point, okay? Couples have no dependence on the about point. Okay, so a couple just is what it is no matter what you choose as the about point. You can just think of it as a pure moment that you just add on to the sum of moments. I try not to go overboard with proofs, but I am going to do this proof because it shows really clearly what happens to the dependence on the about point. So let's say that we have a random body, okay? And we have these two equal and opposite forces. I'm going to call one of them the force vector F and one of them the force vector negative F. And it doesn't matter which one you call which. I'll call this F. That makes this one negative F. Okay. And I'm going to choose an about point to start with. And what we're going to see is that, the dependence on this about point disappears from the calculation. And what that says is, doesn't matter where we put the about point, the answer is the same. Okay. I'm going to call the place where the force F is applied P1, and where the force F, negative F is applied, I'm going to call P2. Or I could call it F, maybe this makes more sense, call it P plus and P minus. That does make more sense. I'm going to do that from now on. Okay, so what is the moment produced by this pair of forces? Well, the moment produced by this pair of forces is just the sum of the moments produced by the two forces, right? So we have this row vector, I'll call this row plus, like that, and a row vector row minus, like this. Row is just the vector that goes from the about point to the point where the force is applied. And now I'm going to calculate the moment. So the total moment about A, because we still have that dependence on the about point we chose, is equal to rho plus crossed with F, and then plus the moment rho minus crossed with negative F. Okay? So that's the definition of the moment produced by that couple. And now I'll expand that. So rho plus is P plus minus A, and we're crossing that with F. And then we're adding that to rho minus is P minus A. And this is crossed with negative F. And now we're going to use some properties of the cross product. I'm going to first distribute these out. So we have P plus crossed with F minus A. That should say F, not A, sorry. Minus A crossed with F. And then plus P minus crossed with negative F. Minus A crossed with negative F. And you can pull the negatives out of these cross products. So I can rewrite this as P plus cross F minus A cross F. Now this is minus P minus cross F. I pulled the negative out to the front. And this one we have a double negative, so this is plus A cross F. You can do all those things with a cross product. And now you can see that the negative A cross F cancels with the A cross F. And we can rewrite this as, in its simplest form, you could write this as P plus minus P minus, all crossed with F. And now I'm going to write this as the moment of the couple. I'm going to leave the A off because the key thing is that it doesn't depend on A. All the A's in that calculation disappeared. Okay, so when you're writing out the table, so let's say, so we have our rho, our force, and our moment. You can always just write the couple as, negative 56 Newton meters. Okay, and these two are irrelevant for the couple. The force is irrelevant because you're adding up two equal and opposite forces, so they add up to 0 force. And the rho is irrelevant because you don't care what the about point is. Okay, so moments will pretty much always be given to you just directly as a couple that you just add on to the other couples going on. Okay, now I want to say one thing we're getting pretty close to being able to start doing problems. I want to say one thing about why, for now, and for almost this whole class, we're just going to be dealing with two-dimensional motion of rigid bodies. So we're only dealing with 2D motion of rigid bodies for maybe the whole class, maybe almost the whole class, depending on how far we get. So why is that? Well, in a 2D motion of a rigid body, so let's think about two instants as a rigid body like moves around, rotates around. Let's say at the first instant, we'll think of this as our coordinate system, okay? And the z-axis is coming out of the page towards us, okay? And then some amount of time goes by, and now the body is oriented like this. And our coordinate system is this. The only component of moment of inertia, so the only moment of inertia component that we care about in this 2D motion is the moment of inertia about the z-axis, okay? And these two orientations, this thing has the same moment of inertia about z in both, okay? So let me say comma, and iz doesn't change from this motion. Okay, if you calculated I sub z for these two things, you'd get the same thing. Okay, but now let's think about it in 3D. In 3D, so if you go from I guess I used a different color before. Okay, so you start out like this. And let's say you go to an orientation like this. Okay. Well, this three-dimensional motion changes every component of the moment of inertia. And what that means is you can't use the equation like this. You can't use the moment is equal to I alpha, because that I is changing. Okay, I loses its meaning. And so you have to use a more complicated approach when you go to 3D, okay? There aren't that many places in mechanics where going from 2D to 3D fundamentally changes things, but this is one of those places. Anybody have any questions about that? I mean, if you don't care, that's fine. But just remember that we're pretty much just doing 2D problems. But this is why we're pretty much only doing 2D problems. Okay? Yep.
And after rotating in 3 dimensions, it's still only moving a plane. So why not just orient the coordinate system with that plane?
Yeah, well, you know, really, that's a really good thought, and that is kind of how you go about changing to 3D. But then you have to deal with the fact that the coordinate system is rotating, you know, which, you know, I've mentioned causes its own problems, you know. Okay, so let me give you a set of general steps for doing rigid body problems. So general steps for 2D rigid body kinetics problems. First, ask yourself, does the body have a fixed point? Is the body connected to the ground by a pin joint or a ball and socket joint? If it does, then that's your about point. If it doesn't, then the center of mass is your about point. Second, calculate the moment of inertia, I sub A, for the about point from step 1. Third, draw a free body diagram. Fourth, determine all the forces and moments. And remember, you're calculating the moments around the about point from step 1. This is where you write out the table. You don't have to do that, but I think it really does help. And it helps too if you make a mistake. You find out you made a mistake later. It's very nice bookkeeping for going back and correcting just the things that you need to fix and knowing that you're not leaving stuff off. Okay, step 5. This is in parentheses because you don't always have to do it. This is only if the about point is the center of mass. Then use Newton's second law. And this will give you 2 equations. And then 6, this you'll always do, use rotational Newton's second law. So that says that the net moment, well, you know what that says. I guess I didn't write it above. And in the plane, this will give you 1 equation. Yes?
Yeah, use rotation Newton's second law if the fixed point is not the center of mass.
This is always. Yeah. And then from there, you might have to do other stuff, but this is the stuff that you always have to do for a rigid body problem. Okay. So let me do an example problem. I think I can get this done. So let's say we have a rigid body connected to the wall by a pin joint. And let's say the length is 2 meters. And this is the point P. And let's say this is released from rest. And we want to know what's the acceleration of that point P. Okay, so the first thing we have to do is figure out whether there's a fixed point. Is there for this one? Yes. So the about point is the pin. So that means that step 2, we have to calculate the moment of inertia around that pin. We're treating this like a slender rod. So the moment of inertia about the pin, that's our I sub A, is the moment of inertia about the center of mass plus md squared. So that's 1/12. I didn't give a mass, I meant to. So let's say the mass is 10 kilograms. Yep.
What makes this a slender rod?
Just that I didn't give a width dimension, so that means that it's small enough that you can ignore the thickness. But I think I mentioned last time a ratio of 10 to 1 is a good sort of rule of thumb value. So that's saying that this thickness is less than 0.2 meters. So we have 1/12 times 10. Computer. Times the length squared. And then plus 10 times, now this distance is the distance from the center of mass to the about point. So what's that distance?
1 meter.
1 meter, yep. And so this comes out to be 10 plus, so 4, what's that? So 1/3, so that's 3.33 plus 10, so this is 13.3 repeating. Okay. And now we'll go to a free body diagram. The weight force acts at the center of mass. So that's 10 times 9.81. The pin joint applies a force with an unknown direction. So I'll just write this as R. Now we've dealt with the weight. We've dealt with every place where the surroundings make contact with the boundary, so we know we're done. And so now we can start filling out the table. Okay, I'll start with the force R. So our about point, I'm just going to put a dot here showing where the about point is. The about point has to be where you chose it in step 1. So in this case, it's at the pin. So what's the vector going from the about point to where that force R is applied? 0, yep. And that force is Rx, Ry. Cross product is 0. And now we'll go to the weight force. So what's the vector from the about point to where the weight force is applied?
1, 0.
Yep, 1 in the positive x, 0 for y. The force is 0, negative 98.1. The cross product is 1 times negative 98.1 minus 0 times 0. So this is just negative 98.1. And now we have this table that gives us all our forces here, all our moments here. Okay, now we're to that step 5 that we do sometimes and not other times. Do we use Newton's second law here? No, there's no Newton's second law. Because there's a fixed point. Okay, so now we go to step 6. That's rotational Newton's second law. And that says 0 minus 98.1, I'm just adding those all up, is equal to 13.3 repeating times alpha. And so alpha is equal to negative 7.36 radians per second squared. Or in other words, the angular acceleration vector of this body is 0, 0, negative 7.36. Okay. Now that gave us the angular acceleration. We're done with the rigid body kinetics. How do we calculate the acceleration of that point P? Well, now it's just rigid body kinematics, and we're just going to use the watermelon equation. So the acceleration of P is just equal to alpha cross R plus omega cross quantity omega cross R. I said that this started from rest, so this one all goes away. And I'll just write out a value here for you, and then if you want to try this, you can. So this just gives you 0, negative 14.720, or 0, negative 14.72. Okay, that's all for today.
What would